In this video, we're going to talk about the area under a curve. In our last video, we talked about integrals, and the title of our last section was Indefinite Integrals. We haven't actually made sense of that word, indefinite, yet, so let's talk about that first. We're going to see the difference between an indefinite integral and a definite integral. So an indefinite integral is the sort of integral that we were looking at in our last video, something like the integral of x cubed dx, for example. A definite integral is different because we actually put numbers on the integral. So you'll see something like the integral from 5 to 6 of x cubed dx. And we're going to make sense of definite integrals in this video. We're going to see how to calculate them, and then we'll see how they help us calculate the area under a curve. Let's try a quick example to see how we go about calculating definite integrals. So the idea is to find an antiderivative for our integrand in a similar way as we did in our previous video. So finding an integrand to x would integrate to give us x squared. For x cubed would become x to the fourth, and any constant just becomes that constant times x. So we'd have x here. Now, we got into the habit with indefinite integrals of writing the plus c, and we're not going to do that here. We'll talk about that in a minute, but we won't do that here. What we are going to do is we're going to evaluate our antiderivative at 5, and then we're going to evaluate at 1, and we're going to calculate the difference between those two numbers. So let's plug in 5 all the way through here. We'd have 5 squared plus 5 to the fourth plus 5. And then we're going to subtract off whatever value we get when we sub in 1. So 1 squared plus 1 to the fourth plus 1. So in other words, we have 655 minus 3 gives us 652. And that's the value of our definite integral. So a definite integral gives us a number, whereas we saw in our previous video, indefinite integrals give us a function. Some sort of function plus c. So let's talk quickly about why we didn't need the plus c. So the comment is, don't write plus c for definite integrals. So anytime you see a number like this above and below your integral, you're not going to write plus c. And the reason why not is because the c would cancel out. So let's see what would happen if we did write a plus c. So if we had calculated our antiderivative and we said it's x squared plus x to the fourth plus x plus c, and then we decided to evaluate that at 5 and then at 1, then our calculation would look like this. We'd have 655 plus c, and then we would subtract off the value at 1, which would be 3 plus c. So those c's would just cancel right out, and you would just end up with the same answer as we got before, which is 652. So it's not actually wrong to write plus c. It's just extremely inefficient because the c is going to cancel out. So therefore, the convention is you don't write plus a constant when you're working with definite integrals. So for indefinite integrals, we must write plus c. For definite integrals, we don't bother. It's not necessary. Let's try one more example, and then we'll see what they're useful for. So first thing we're going to do is find an antiderivative for our integrand. Power is going to increase, divide by the new power. So we've got x to the fourth over 4. And that's going to get evaluated at the top number and then at the bottom number. We're just going to subtract. So subbing in 3, we'd have 81 over 4. And then we're going to subtract off the value that we get at 2. Subbing in 2, you'd have 16 over 4. So altogether, our answer is 65 over 4 for the value of that definite integral. So let's see a fact here that explains why definite integrals are so useful to us. I've just erased the picture that's in the notes because I want to draw that fresh just as we talk about this. So imagine that you've got a function that is greater than or equal to 0. So meaning you've got some function that never dips below the x-axis. Okay, we could draw a picture. Let's say over this region, our function maybe looks something like that. So that's y equal f of x. Let's suppose we wanted to calculate the area under our function. And when we say the area under our function, we mean the area under the function and above the x-axis. So we're talking about this area here. Saying the area under y equal f of x is just a fast way of saying area between the function and the x-axis. Okay, and let's say that we want to do that just for a certain section of the x-axis. Let's say between x equal a and x equal b. So this is x equal a, that's x equal b. So we got this area, I'll just color it in red here. This area is actually represented by the value of the definite integral. We're integrating the function f of x, and we're integrating from the values a to b. So now we're starting to understand what these numbers on the integral represent. They're x values. They're telling us that we're looking at the area under our function between x values a and b. So that's what the definite integral does for us. So let's find the area under y equal x squared from x equal 1 to x equal 2. If you want, we could draw a quick sketch just before jumping into this problem. So we're talking about the parabola. Passes through 0, 0, 1, 1, 2, 4. So we've got this sort of parabola. And we're looking at the area under this parabola, so the area between the parabola and the x-axis, just over that region where x goes from 1 to 2. So just from eyeballing this, you might say, oh, that area looks like maybe 2 or 3 units. Let's use a definite integral to figure out the exact area. So to get the area, we're going to integrate the function, which is x squared. We always write dx at the back of any integral, and we'll actually talk about that a little bit later in this video. And then if you want to represent that you're integrating from x equal 1 to x equal 2, just put your x values on the integral. Smaller x value should go at the bottom and the bigger one should go up at the top. Okay, so then we find an antiderivative for x squared. So we're going to bump up the power, divide by the new power, and then don't need a plus c because it's a definite integral. And then we will evaluate at 2 and then at 1. So plugging in, you'd have 8/3 minus whatever value you get by plugging in 1. So that would be 1/3. So overall, our area comes out to 7/3. And I would say that seems reasonable according to our sketch. We said that area looks like it's going to be 2 or 3 units. So 7/3 fits right into that range nicely. So let's try one more area calculation. We're going to find the area under y equal 1 over root x from x equal 4 to x equal 9. Well, again, if you like, you could draw a sketch. Certainly not necessary to solve the problem, but you might just feel like a visual here. So we're going to sketch the function y equal 1 over root x. So I've just indicated some of the nice x values that we might want to work with here, which would be x equal 1, x equal 4, and x equal 9. So at x equal 1, the value of our function is 1. At x equal 4, it would be 1/2. And at x equal 9, it would be 1 over root 9, or in other words, 1/3. I've actually got y values up here, coming down to 1, 1/2, and then 1/3. So that's what our function looks like. Now we want to find the area under that function, just between x equal 4 and x equal 9. So we're talking about this little area in here, the area between our function and the x-axis over that range of x values between 4 and 9. So let's try it. If we wanted to calculate the area, we'd say, well, let's use a definite integral from 4 to 9. We're integrating our function, the 1 over root x, with respect to x. So first thing you might want to do is just rewrite that function into exponential form to make it a little bit easier to do the integration. So you could call it x to the minus 1/2. And what we're going to do is bump up the power. It's going to become x to the 1/2, divide by that new power. So dividing by half is like multiplying by 2. And remember, you don't need a plus c for a definite integral. What you do need to do is plug in 9 and then plug in 4 and just subtract those values. So let's try it. We're basically saying 2 times root x is what we're subbing into here. So when we sub 9 into that, it's going to be 2 times 3. And then when we subtract the value at 4, it's going to be 2 times 2. So overall, our area comes out to 2. And just from looking at our rough sketch that we've got up at the corner here, the top right corner, I would say, yeah, that's believable that that area could be 2 units. So at this point in the video, we've seen how to actually evaluate a definite integral, and we've also seen what it represents. So let's take a step back and think about 2 of the big ideas that we've seen so far in our course. We saw very early on in the course that when you take the derivative, what that gives you is the slope of the tangent line. So we're going to think about that in a little bit more detail. And we've just recently seen in this video that the definite integral gives area under the curve. Now, what's interesting here is that differentiation, the process of taking a derivative, and the process of taking an integral are inverse processes. They undo each other. What's a little strange from an intuitive point of view is how are slope and area inverse ideas? So without getting too technical, I just really want to get to the intuition behind this and try to answer the question as to how calculating a slope and calculating an area can be inverse processes. So let's talk about the derivative first, because that's what we're more comfortable with. We've spent more time thinking about that. So if you want to take the derivative of a function y with respect to x, you might call that dy by dx. And if you think back to our discussion on differentials, you might remember dy represents a little change in your y value and dx represents a little change in your x value. So if you were to draw a picture of this, you could say, okay, we've got some function here and we're looking at 2 points that are quite close together. And we're saying as you move between this point and that point, you're getting a little change in your x value, which we could call dx, and a little change in your y value, which you could call dy. Now, if you take the ratio, if you go dy over dx, what are you really doing? Well, you're doing basically rise over run. So in that sense, the derivative is going to give you slope. So we could actually draw that in the picture. Dy over dx would give us the slope of that little line segment. So if you wanted to get formal about this, you could say the slope of the tangent line is actually the limit as your run goes to 0 of your rise over your run. Now let's talk about the definite integral. So we saw in this video the actual notation we'd use for that. We'd say it's the integral from a to b of some function f of x times dx. And let's try to get a sense of what this notation really represents. So imagine that you've got some function. Here's our function y equal f of x. And let's say you're interested in looking at this function along this little interval from a to b. So what this integral represents is a sum. We could say this is a sum of many tiny areas. Okay, and what are the areas? They actually have area f of x times dx. So let's see if we can visualize that in our picture. So what is dx? It's a little change in our x value. So we could say that's dx. If you multiply dx by the height of the curve near those x values, then you actually create the area of a rectangle. And as long as you're taking quite a small change in your x values, then your function won't be changing very much over that interval. So that's why it's pretty much safe to say f of x, because essentially the function is going to look almost constant over that little interval. So f of x times dx is just the area that we've shaded in here. It's the area of that rectangle. Okay, so what would happen if we took the sum of many of these tiny little areas f of x dx? Well, you can imagine just filling in your whole area here under your curve with many, many of these tiny rectangles. So I'm just going to shade them in sort of different ways so that you can visualize that there are many of them here in our picture. So what the integral is actually doing is taking the limit as the number of these rectangles goes to infinity of the sum of these areas. And what that gives you is the total area under the curve. All right, so now we've had a reminder of why does the derivative give slope? Well, it's because it calculates dy over dx. And we've talked about, well, why does the definite integral give area? Well, that's because the integral is essentially a sum of things that look like f of x times dx, which are little rectangles, areas of rectangles that are being summed up. Okay, so to answer the really deep question here, which is how is taking a derivative and taking an integral, how are those inverse processes? Well, essentially what this boils down to is taking a derivative, in a sense, is like doing a division, because you're dividing rise by ren. And taking a definite integral, in a sense, is like a multiplication, because what are you doing? You're multiplying the value of your function times that little small change in x, and then you're summing up those things. So in terms of units, derivative has units of division, and an integral has units of multiplication. And in that sense, taking a derivative and taking an integral are inverse processes. So that's all about definite integrals. Thanks for watching.